Hi everyone. Okay, so this is the video for this week. So we skipped the class on Tuesday, and this is the recording for the Thursday's lecture. So first of all, I would like to remind you about assignment 2. Yeah, you need to submit it by October 10th. And please read the instructions as in the provided PDF. It's exactly the same format as assignment 1. One thing I would like to say is this assignment is slightly more challenging. There is this part about writing to file. I think it's a bit more challenging. Maybe it's not. I don't know. Anyway, but please don't postpone things until the last day. Okay, so here's the plan for today. What we're going to do today is talk about the big O notation. And just to motivate this big O notation, so last time um, we 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 talked about measuring performances of algorithms. And we saw these three problems. So one is computing given two numbers with n digits each, compute their sum, compute their product. And there was a third problem, which is kind of the opposite of computing product, sort of given a number, break it into p times q. And for each of these questions, we asked what's the running time of our algorithms. Okay, so just to remind you, maybe I'll actually do it here. Um, oh yeah, I actually have it here from last time. So suppose we have, I don't know, two numbers, this number and this number, and I don't know, let's make it longer. And our goal is to compute their sum. So how do we compute the sum of these two numbers? Well, the usual way to do it is we compute the sum of the units, right? We do long addition. So it's 5 and 2 plus 8, it's 0, and there is a carry of 1. And then 1 plus 9 is 0, is 10, and plus another one, that's 11. And there's another carry. And then 9 plus 8 is, 17 plus 1, it's 18, and we have a carry of 1, so we have a carry here. I think we have a carry here also. So 5 plus 6 is 11, plus 1 is 12, and yeah, so somehow we have a lot of carries. Anyway, so I think I'm pretty sure you know how to do long addition, and we ask what's the running time of this of long addition. And long addition can be done in in maybe 2n operations, or maybe 3n. I don't know. For each pair of digits, we need to compute their sum and then have the carry. So, or 3n or something like this. Right. So what about multiplication? So multiplication is maybe more complicated, right? So let's say we want to multiply this by that. Do you remember how to do this long multiplication? So right, so multiply 4 by 3, that's 12, I guess, and we have a carry of 1, and 8 times 4 is 8, plus 1 is 92, and then we multiply 5 by 23, that's, yeah, it's a hard exercise. Something like this, and then we need to compute the sum of these numbers. So we have 2 and 9 plus 5, that's 14, and we have, I think this is the correct result. I don't know, maybe I'm wrong. And we asked what's the running time of this algorithm, and we said, well, observe that if this number has length n and this number has length n in n digits, then we will have n rows here. And each row will be also of length n, or maybe a bit longer than n, right? And we have all these shifts. So the total running time is something like n squared. So long multiplication can be done in approximately n squared time. And this approximately part, it's not very clear. So is it 2 times n squared, 3 times n squared, maybe 2 times n squared, or 3 times n squared, and then there is this adding up all these rows at the end, which would take another n squared times, or maybe 4 times n squared. So anyway, I don't know exactly. So the goal of this big O notation is exactly that, is not to worry about the constants, because I will try to say that they are not very important. Okay. So we will use this big O notation. So, okay, so here's what we're doing now. We'll use big O notation to express the running time or the time complexity of our algorithms. And, suppose we have on input of length n, fn is our running time. So maybe for multiplication of two numbers, the running time is 1.5 n squared plus 4n plus 3. And maybe for another problem, it's 2 times n to the 4 plus 10n cubed plus, some other terms. Or, maybe there's another problem that takes exponential time in n. Right. And it's kind of annoying to say that, oh, yeah, the running time is this really long expression. We would like to say, you know what? All I care about is the fastest increasing term in this sum. I don't care about every term, but only about the fastest increasing term. So as one example, I'll say, let's say fn is this 2 times n to the 4 plus 10 times n cubed and so on. We'll say that the time complexity is O of n to the 4. So what I'm saying is we're going to ignore multiplicative constants. So this 2, we're going to ignore it. And we're going to ignore all low order terms. Okay. And let me try to actually motivate this. I have to say that, maybe these low order terms are not that important. And here is how I'm going to do that. So I'm going to write this expression 2 times x to the 4 plus, was it 10 times n cubed plus, okay, I'll write plus 4 times x squared. I will not write, oh, it should be x everywhere. And the other one will be simply 2 times x to the 4 and maybe also 3 times x to the 4. Okay. Right. And then I'll need to do a nice scale. So let me, let's say from 0 to 100. And here I need to go from 0 to that. Perfect. Right. So what are we seeing here? So red is the actual running time. And blue and purple are these bounds, bound from above and bound from below. And well, look, if you look from really far away, you look for large values of n, then it's sort of, if I write simply 2 times x to the 4 or I write the actual function, it makes very little difference. And if instead of 2 I put a 3, then it will be above it. Okay, so the 3 times x to the 4 will be more than our function. Okay, so this is our function, right? The red one, and the blue and the purple are sort of upper bounds on it. And what I'm trying to say, if I look from really far away, maybe up to 1000 actually. Let's try. Right. Well, we can't even tell a difference between red. If I zoom in, yeah, we'll see red, but we cannot tell a difference between red and this one. So this is what I'm going to try to do today. Okay, we're going to kind of try to define this definition of big O notation, make this definition of big O notation so that we can ignore all these low order terms and also kind of ignore the constants. Okay, that's the goal for today. Right. So we said, we're ignoring low order terms because, in this picture we saw that they're negligible. And, if we try to look at this picture, this is f of n. Okay, so let's say this is f of n. And if you look at n really large, well, when n is 100, maybe the 100 n cubed still makes a difference. But when n is, let's say, on the order of millions, then we already see that n to the fourth is larger than all other terms, by a huge factor. Right? So even if we had n to the 4 compared to n squared, even if n squared is multiplied by a huge number, when the inputs become really large, still this is the dominant factor, the n to the fourth. Okay, so what I'm trying to say, the dominant factors are the important ones, and everyone else, yeah, we can sort of ignore them because for large n's, then they don't make a difference. Right. And another question you might ask, why do we want to ignore the multiplicative constant? Right, so here I'm kind of going to say, you know what, the 4 times, I don't care if it's written here 4 or 3 or 1, it's all the same to me. And the reason for that is the following. Look, let's say I have a multiplicative factor of 2 there. Okay, so it's 2 times n to the 4. If I buy a computer that runs twice as fast, or maybe has, better setup of the, in the better configuration, then we can increase the running time maybe by a factor of 2. On the other hand, the n to the fourth, it's not something that we can change by buying a faster hardware. Okay, so we cannot increase the run, we cannot make it run faster by a factor of n. It's just not how it works, right? So we can make the computer run faster by a factor of 2. Each operations will be twice as fast, but you cannot make it n times as fast because computer doesn't know what's n that we're looking for, right? We'll try different n's. So what I'm trying to say is, for us, so only for this course, okay, only when we talk about big O notation, also the multiplicative constant doesn't make a difference. In practice, constants do make difference. Of course, if I have an algorithm that runs twice as fast as the other one, yeah, that's faster. But we'll kind of pretend that in theory. So in theory, we ignore them and we only care about the, what's the polynomial or what's the running time? Is it n? Is it n squared? Is it n log n? And so on. Okay, so that's the motivation, and now we'll go move to definition. So, right. So here's what I would like to say. So we'll have f. F is our actual running time, and g will be the bound that we want, right? We want to say f is order n squared. Or maybe if f is the running time of sorting algorithm, g will be n log n. And I would like to say that g is that f is order of g. So O is order or upper bounded by g. I would like to write this when I mean that f is essentially smaller than g. That it's smaller than g if you ignore all these, if you ignore the multiplicative constants and ignore the lower order terms. Right, so here is a naive attempt. Let's try to define f equals O of g. If f of n is less than g of n for all n, if two functions are just f is always smaller than g. So why is this a wrong definition? Because, for example, let's say we have, for this problem of adding two large numbers, of length n. So the actual running time is 2n. We would like to say that fn is O of n, okay, because we want to ignore the 2, but it just doesn't fit this definition. So this definition is incorrect because it's not true that f is less than g for every n. Okay, so this first attempt for defining f is less than g if simply pointwise, for every n it's less than g, this is not the right definition because it kind of I wanted to ignore the factor of 2, but it doesn't. It just says, f is less than g for all n. So it doesn't work. Okay. So how about we try to, modify the definition. So we'll have another wrong definition, but, wrong, but kind of, instructive. So here is wrong definition, second attempt. We'll say that f is O of g if f of n is less than 2 times g of n. Oh, that's great. Then it fits this example. But wait, but if f is, let's say, 3 times n, then it doesn't work, right? Because it's not true that fn is less than 2 times n. So given these two wrong definition, what we want to say, we don't want a specific constant, like f is less than 2 times g, but instead we want to say there exists a constant. So here is the correct definition. So we have two functions f and g, and would like to say that f is upper bounded by, or essentially upper bounded by g, if there exists a large enough constant c, so maybe c is like 10 or 100 or 1000, such that f of n is less than c times g of n for all sufficiently large n. Okay, so c is not necessarily 2, c sort of depends on what's the formula for f. Maybe another way to see it is, it's an equivalent definition. Let me divide both sides by g of n, and here's what we'll get. So f, we define it to be order of g, or essentially upper bounded by g, if there is some constant c such that f divided by g is less than c for all n large enough. Okay, so what does it mean, all n large enough? It means that, maybe when n equals 1 or n equals 2 or n equals 5, this inequality doesn't work. But when n is large enough, this inequality holds, that f divided by g is less than c, right? So we have the f function, we have the g, and if we take f divided by g, it's always upper bounded by some constant, right? It's always less than 10. So f is less than 10 times g. That's our definition. Yeah, and if you like calculus, I suppose it would say something that, you take f divided by g, you look at the lim sup when n goes to infinity, and it's upper bound. If you got it, fine. If not, yeah, don't worry about it. Let me show you one example. Okay, so I'm just going to show it using a formal definition. So I'm going to show that this function, so we take fn equals 1.5 n squared plus 4n plus 3. I want to show that it's O of n squared, and would like to show it using the formal definition. Okay? Right. So intuitively we say, because the important term here is n squared, and these other terms are not important. So that's exactly what the definition is trying to capture, and let's see that. So let's take c to be, this magical number 8.5. And I want to show that, what does it say? We say that f is O of g if there exists some constant, the constant is 8.5, such that f of n is less than c times n squared. Let's try. So I write f of n simply as the definition, 1.5 n squared plus 4n plus 3. Okay, and I would like to upper bound it by c times n squared. So what do we do? Well, let's see. I just copy 1.5 n squared as is. 4n is less than 4 times n squared, and 3 is less than 3 times n squared. So now all terms are n squared, and we can just sum them up. We get 8.5. We didn't have to take 8.5. We could take c to be 9. In fact, if you ignore a few small values of n, we can make we can take c to be 2, for example. Let me try to show this. So maybe in Desmos, it's a good, yeah, maybe it's a good exercise to do. So what was exactly, so f of x is 1.5 and x squared plus 4x plus 3. Okay, so this is our function. Let me do some scaling here. I don't know, 1,000, let's say. Right. Okay, so this is our f. And if we take something like 2x squared, then it's always above, not always. Okay, so if we look at really small values of n, maybe it's not true. But if we take x to be large enough, we take n to be large enough, then f is always upper bounded by 2 times x squared. In other words, if I take x squared, and if I take f and divide it by x squared, so look at this one, it's always upper bounded by, close to 1.5. So it's upper bounded by 2, except for really tiny values of, for all x greater than 10 or something. Okay? So again, one way to see it is to see that f, our actual function, is less than 2 times x squared. Another way to see it is you take f, you divide by x squared, and you see that it's less than 2 for all sufficiently large values of n. Okay, I hope this part is kind of clear. Um, right. So again, this is just the formal definition, and let's try to do these exercises. So why is it true? So okay, so this one we show that it's true. What about this one? So actually, this is also true that f is order of n cubed. Why? Because, it's less than, well, we saw that it's less than 2 times n squared, and n squared is less than n cubed. So, f is also less than n cubed. Right, so if we put, say, n cubed here, so if we put n cubed, then it's even larger than f. Right, so the point of this example is to say, when we say that f is O of this other O of n squared or O of n cubed, it doesn't mean that the bound is tight. Okay, it means it's just an upper bound. It means that f is essentially less than whatever is written inside. N cubed essentially means up to a constant and for large enough n, but it doesn't mean that the bound is tight. Sure, we would like the bound to be as tight as possible, but that's not necessarily true. Yeah, again, this is also true because 2 to the n grows even faster. On the other hand, this one is false. So why is this one false? Because, well, we have the n squared term, and if you look at f divided by n, it actually goes to infinity, right? It's not upper bounded. So let me write it. Because f of n divided by n goes to infinity. Right. Right. So it's not upper bounded by some universal constant c. It's not, we cannot choose some constant c, like 2 or 10 and say that f of n divided by n is less than c. No, it just grows. So it means that it's not true that f of n is less than n. Okay. So I hope, and similarly these examples. Okay. So let me do some constant common orders of magnitudes. So the simplest one is O of 1. So these are, when we have a function whose running time is O of 1, that's the best. the best in the sense that the running time is simply constant. So we make no more than 10 operations. Okay, so that's what O of 1 means. So log n, yeah, logarithmic complexity is very fast. So for example, we know binary search runs in time log n. So log n basically means you don't even read, if you have n bits, you don't even read the entire input. You read only log n bits from the input, which is, yeah. Reading less than everything, it's fast. Next is O of n, which means linear in n. So that's uh, O of n, again, it hides some constant, right? Which means for every bit of the input, we perform like two operations or something. So it's constant times the size of the input. Okay, so maybe 3 times the size of the input. Oh, there is, n log n. So log n grows kind of very slowly. So n log n is, almost as good as linear, and then this n squared, and then to the fourth, and then to the seventh, and then there is exponential in n, and depends on the base of the exponent. So 4 to the n is even worse than 2 to the n, and n factorial is even more, and yeah, and so on. Okay, but I think, we'll usually be somewhere here. Maybe sometimes we'll have something exponential in n. Basically, n squared or n cubed, these are the feasible algorithms. 2 to the n, they're feasible only for, kind of small values of n no more than like 100 or so. And if you go here, it becomes completely infeasible even for small values of n. Okay. Oh yeah. Here is a question for you. So maybe you pause for a second and think about it. Can you explain to me what's log n? So explain to me in simple words, like I know nothing about, yes, I can draw the function and so on, but, without drawing the function, what's log to the base 2 of n? Uh, so I guess, x equals log to the base 10 of n means, 10 to the x is equal to n, right? That's the definition. But can you explain it in simpler words? Okay, so here's what we do. So what's log to the base 10 of 100? That's 2. What about log to the base 3 of 1000? That's 3. What about log to the base 3 of 1 million? I guess that's 6. What about logs to the base 10 of, I don't know, of this number? And, yeah, I don't expect you to maybe I don't put a 6 here. I put like a 9 or 4, whatever. I don't expect the exact answer, but close enough would be 6 point something. Okay. So basically, what I'm trying to say, and if it's log of 10 millions, then it's 7. And if it's, I don't know, 43 or something, then it's 7 point something. So what I'm trying to say is log to the base 10 of n approximately counts the number of digits in n. Okay, so if you can remember one thing, from today's lecture, log to the base 10 of n counts approximately counts, right? Not exactly, but it's off by 1. Counts the number of digits in n, which means it's a really small number. If a number is a million, the number of digits is only 6, or okay, it's 7. Okay, so this shows that log n grows really slowly. Right, so there's an example here, log of 200, it's between 100 and 1000, and for 1003, for 100, it's 2, so it's in between them. So it approximately counts the number of digits. Right. Let me make it a bit more. So here are some simple rules. uh, if we take, n squared and n to the 4, yeah, it's true that n squared is essentially smaller than n to the 4, but in the other direction, it doesn't hold, right? Because n squared divided by n to the fourth divided by n squared goes to infinity, while this one is upper bounded. Log n is smaller than any power of n. Okay, so log n is less than n to the, I don't know, to the square root n or n to the 0.1. Another important rule is this rule of logarithms. So if you look at log base 2 of n and log base 10 of n, they are off from each other by this exact factor. And what's this? Well, you can go check what it is, but it's some number between 3 and 4. So, if instead of 10 it was an 8, we would have 3. If it was 16, we would have 4. So it's in between. My point is, when I write O of log n, we don't need to specify the base because the constant in the O notation will simply hide this factor. So I'll simply write O of log n, and it's fine, and it doesn't matter what's the exact base. Let's do some simple exercises. Okay, so here are some exercises. I'll do one of them, and you'll do the other two. So let's say that f is O of g, and g is O of h, and f is O of h. So yeah, let's try to parse it. So f is essentially smaller than g, up to multiplying g by a constant. And g is essentially smaller than h, up to multiplying h by a constant. Then f is essentially smaller than h. No, f is less than g, or less than 10 times g. G is less than 5 times h, which means that f is less than, some constant times h. Convince yourself about this. Okay, do this exercise for me. Which one am I doing here? Okay, so another one will do, if I have two functions f1 and f2, and each of them is less than O of n squared, then their sum is also less than O of n squared. Okay, so I have two programs. One runs in times, I don't know, 3n squared, the other one in times 4n squared. Then if I run both of them, the running time is still order n squared. Right, and in fact, the sum is less than the maximum of the two functions. Okay, let's do this second claim. Okay, so here is the claim. I have two programs, one runs in time f1, the other one in time f2. And I know that each of them is upper bounded, the running time is upper bounded by order n squared, let's say. So let's say g is n squared. I want to say that if I run both programs, one after the other, then the running time will be also O of n squared, although with a different constant hiding in O. And we do it simply by definition. Okay, let's get you. So we're getting used to this definition. Right. So we have f1 is order g. Okay, that's our first. So what does it mean? It means that there exists some constant c1 such that f1 is less than c1 times g for all n large enough. So what does it mean n large enough? There is some, little n1 such that for all inputs of length more than n1, f1 is less than, this c times g of n. Okay, that's the definition. That's just by definition of f1 is upper bounded by, essentially upper bounded by g. It's order of g. Same thing with f2. F2 is order g, means there exists some constant c2 such that f2 of n is at most c2 times g of n, maybe not starting from n equals 1, but only starting from n, some other constant. So we need to skip the first 10 numbers or first 15 numbers, and then f will be less than c2 times g. Okay, so this is the definition of the first one and definition of the second one. Okay, what's the conclusion? We want to conclude that their sum is also upper bounded by some constant times g. How will we do that? Well, we take c to be just the sum of these, we take f1 plus f2, So first is less than 2 times n squared. Second is less than 3 times n squared. Yeah, take their sum. So take C to be C1 plus C2. Then F1 plus F2 is less than, right? So F1, we know that it's smaller than C1 times G. F2 is less than yeah, F2 is smaller than C2 times G. C1 plus C2, this is exactly the C that we took. Oh yeah, and all this is true assuming that n is large enough, right? So the first one was assuming that capital N is greater than 10. This is assuming that capital N is greater than 15. So we need to take the maximum, right? So we need to skip the first few small numbers and we get this, right? So the conclusion is that for all large enough n, f1 plus f2 is upper bounded by some constant times g, or what's this constant? It's just the sum of these two constants. Okay, I hope you're getting this. Right. So the conclusion, this exactly means that f1 plus f2 is less than c times g for all sufficiently large n, which exactly is the conclusion that we wanted. Okay. Um, how about you do this exercise on your own and maybe you pause, you have a look at it. So I have a bunch of functions here. Oh, I see. Um, and we need to, oh, give me a second. There's some hints here that I would like to hide. And your goal is to sort these functions, let's say in the increasing order. So which one is the smallest and which one is the largest? Okay, so you stare at it for a second, or maybe you pause, you stare at it for a bit, you do this exercise, and then I'll do it with you. So I'll count to 5 and then I'll do it with you. 1, 2, 3, 4, 5. Right. So which one of these is the smallest function? So I guess the smallest one is, f8. Right? Because it's log of n over 2. So do you remember your rules for log of n over 2? This is, this is equal to log n. I'm not specifying the exact log. Let's say it's log base 2. So minus log base 2 of 2, which is just 1. Right? This is just 1. Okay, so this is a small one. What's the next one? So this is log to the power 15. So I suppose the next smallest will be f5. Okay, after f5, what do we have? This is n log n. Oh, this is simply linear in n. Oh no, that's not linear in n. Look what's hiding here. That's 4 to the n. So this is not linear. This is 4 to the n. So this is actually a huge function. Which one is smaller now? So we have n squared here. So that's f1. Yeah, next one is, oh no, there's f7. Sorry, f7 is order n log n. N log n. This one is n cubed. Yeah, maybe that's the best idea. So we'll first write all of them. So that's n cubed log n. This is order 2 to the n. This is order n squared. Okay, so we have, I guess, F7, and then F1, and then F4, F3, F4 and F3. Let's see, what's missing? 1, 2, 2 is missing, and 6. Okay, so 2 is 2 to the n, and this one is 4 to the n. So I think 6 is the largest, and 2 is the one after that. Okay, so I think I solved this little exercise. Okay, I hope you solved it also. Right, so here is another exercise for you. So show that, if you take log cubed, then it's less than n for large enough n. And instead of doing it, let me just show it to you in plot. So we take log base 10 of x. So as you can see, log is a really slowly growing function, and this is x, this is a linear function. But even if we make it cubed, it will not become much larger. Okay, so my point is that x grows faster than log cubed, but also faster than log to the 4 and log to the 6 and so on. So maybe for 6 in the beginning, it kind of looks that it might be growing, but no. If we take x to be large enough, then we'll see that even any power of log grows slower than simply x. And if that's your thing, try to prove it formally, like compute derivatives and stuff like that, if you would like to do that. Okay. So we didn't do any coding today, so I think we should do at least some coding. Okay. And here's what we're going to do: searching. We'll talk about two search algorithms. So searching an array, given we're given an element, and we're given an array, and we want to find an element in the given array. And you might ask, do I have any information about the array or not? So if the array is unsorted, or in general, if we have no information about the array, yeah, what can we do? We can simply do linear search. Namely, we iterate over the, array in position 0, position 1, position 2, position 3, and so on, until we find the element, our element. Or we just read the entire array, we find nothing, and then we just, say not found. So in the worst case, we will be looking at all elements, or maybe the element we're looking for, this is the last element, or maybe it's not in the array at all. So the running time will be O of n, right? So if you have n elements, the running time is O of n. And let me ask you this question: why isn't the running time exactly n? And the answer is, well, it's not exactly n, because let's look at the code will say something like, oh, there's a for loop, and then we want to compare the array to the given element. So it's not exactly n, because there is comparing and there is the for loop, and for loop is not completely for free, right? So the running time is not n, and you can see why it's actually convenient to write O of n, because I don't know how many operations takes this for loop. Is it 2n? Is it 3n? I don't know. Okay, let me try to show an example. Okay, so this is linear search, and the linear search we will not run it on numbers, but rather it will be an array of person. So the person the struct person has ID and name, and we create an array of people. So the first is ID, the second is name. I guess when I wrote it, I was into this Squid Game show, right? So these are some of the characters in the show. So this is the ID and this is the name. Okay, so now for linear search, what do? We get an array of people, we get the length of the array, and we get the ID of the person we're looking for. And here's what we do. So for I going from 0 up to length -1, if array in position I, if their ID is equal to the ID we're looking for, return I. And if we iterated through all the elements and we didn't find the ID we're looking for, then we simply return -1. So why -1? Because we need to return some int, and we don't want it to be 0 because 0 is an index in the array. Right? So we either return the index where the ID is found, and we return -1 if we didn't find it. Right? So if you look here, the running time is not exactly n, because there is, for each loop we have compare I if it's less than n, so that's one operation. There is increment, that's another operation. There is this, comparing the IDs, which is another operation. So maybe it's like 3 times n or something. Okay, so it's not exactly O of n. Right, so that's an unsorted array, and here's what we do for sorted arrays. So if the array is sorted, then actually it's easier to find the element we're looking for. And the reason is, the story that they say is like looking for a word in a dictionary. So we have a dictionary and there all words are sorted. And if I want to find, I don't know, definition of a giraffe, then maybe I'll open it somewhere in the middle and I'll say, oh, giraffe, it starts with G, but I open it at I don't know, K, so I should probably go closer to the beginning of the dictionary. And if I open it B, oh, B is too close to the beginning, so I'll kind of try to open a bit further, and so on. So the idea, we'll try to make it into an algorithm. So the algorithm is kind of a basic example of divide and conquer. So we cut the array into 2 roughly equal pieces. And here's the thing. If the array is sorted, we don't need to search in both parts. Let me try to explain. So we get an array of length n. So here's our array. We look at the midpoint. And we say, well, look, if in the midpoint we have exactly the element we're looking for, hey, that's amazing. We just return the index, this midpoint index. We're happy. What happens if the midpoint we see is larger than the element we're looking for? Well, what it means is the actual element, if it's there, it cannot be on the right of the midpoint, right? Because the elements are sorted. So we only need to look on the left. So we'll look only in the left half of the array, from start up to midpoint. And otherwise, if the element we see the midpoint is smaller, then it means that we need to look at the right side, the right half of the array. Okay, so that's the idea. So the point is each time we cut the array by 2, right? We take only half of the array. So we look at the midpoint. If it's the right element, that's great. If it's greater, then it means we only need to look at the smaller elements which are on the left. And if it's smaller, then we need to look on the elements on the right. Let's see. So what's the running time of this algorithm? So I would like to focus on the running time. I'm sure you've seen binary search at one point, sometime previously. Let's see. Checking the if statement, this is constant time, it's O of 1. And we have a recursive call, but we don't make both recursive calls, we make only one, right? So either the midpoint is greater or it's smaller than the element. So make only one recursive call. So what are we saying? So T of n this is the total running time. T is the time on input of length n, is constant plus T of n over 2. Okay. So we make one recursive call on length n over 2 plus, some constant. Okay. How do we solve this? Well, let's see. T of n is T of n over 2 plus constant. But what's T of n over 2? Again, we split the array by half. We cut the array by half, so we get n over 4. And, this constant, it appears here twice. What about T of n over 4? We divide by 2 and the constant appears 3 times. And so on. After going inside for I steps, the length of our array is n divided by 2 to the I. We divide by 2 once and twice and 3 and I many times. And we pay I times this absolute constant. How many steps will we do until the length of the array becomes 1? Well, the length of the array becomes 1 when I is log base 2 of n. This is exactly the definition of log base 2 of n. It's which I satisfies 2 to the I equals to n. And how many times are we going to pay this, this constant? Exactly I times, which is log n. So the total running time is order log n. Okay, so we make sort of log n iterations or log n recursive calls or iterations inside. And for each of those, we pay constant running time. The constant is basically doing all these if conditions. Okay, so this shows, this is kind of a formal analysis why the running time of binary search is order log n. So one advantage is really fast, but it must, we require that the array is sorted. And, in general, the array may be, okay, if the array is fixed, maybe it's expensive to sort it, and maybe it's dynamic, so we sort it, but then we want to add elements and remove elements and change elements. So, in general, things depend on your applications, but whenever possible, it's nice that the array is sorted. Okay, now I would like to show you this example with a binary search. So we have this array of players. And here's what we do. Here's how we do it. So we'll have the start and the end point. Okay, so we start with, start is 0 and end is length minus 1. And here's what we do. As long as start is less than the end, compute the midpoint. Okay, so just compute the mid index. And, if mid index is exactly the element you're looking for, this is great. Just return this index. Otherwise, if the element we're looking for is less than the ID that we see in the middle, it means that we need to look at the left half of the array, which means start will remain the same, and end we want to shift it, to the left half. Okay. And sort of the symmetric thing, if ID we're looking for is larger than the midpoint, then the endpoint will remain the same, but the start will be shifted to the midpoint. So we each time we take only half of the array. So in each iteration of this while loop, the boundaries, they become half of the length of the previous length, right? So previously it was from 0 up to length, and then we decide to maybe make this half and then this half and so on. Okay, so that's the example. And here I have, this is the list of people, and we run the binary search, and let's try to run it. Okay, so, when we run it, okay, so we get a list of length 8 and 199, Ali Abdul. Okay, so the index returns the actual index. And then we print not only the index, but also the name. So we take list in position index dot name. Right. And if we would like to do some debugging, let's see how this part works. So I'm going to put in each step what's the start and the end point. Okay, so we're looking for this element. And here's what we're getting. So in the beginning, so what are the start and the end point in each iteration? Okay, so in the beginning, we start with 0 to 7. So from 0 to 7. And then, we take the midpoint, and I suppose it says, it cuts it here. So is the number we're looking for 199, is it smaller than the midpoint or greater than the midpoint? So, it says it's greater than the midpoint, so we just reduce it to 47. So we reduce it to this half. Okay. And I suppose in the next step, we'll take the midpoint to be this one, and we'll ask, is the midpoint, right? So between 4 and 7. So we reduced ourselves only to this part now. So this is index 4 and this is index 7. And if this is the midpoint, we'll ask, are we the midpoint? No, we're looking for index 199. Do we need to look before or after? Is the number smaller or greater? So it's smaller because it's 199. So then we reduce to this subarray. The subarray is 4, 4, and then we just find it. Do some debugging yourselves. I think it's a very useful exercise to do, so please do it. And while we're here, I would like to mention that, I presented binary search as a recursive algorithm, but when I wrote it, there was just a while loop. Please write it both as recursive and as non-recursive, and I actually have the file for you here, this one. So here is for linear search, do linear search recursive, do binary search just with the for loop, and do binary search recursive. So this one is simply with numbers, okay, not with person. So it just gets an array of numbers and it tries to find the right number. And also do write some test cases. Okay, so that's all we have for today. So you have some, some practice problems. This you can please do it. All right, that's all. Thank you.